Use strong mathematical induction to prove the existence part of the unique factorization of integers theorem, theorem 4.4.5. In other words, prove that every integer greater than 1 is either a prime number or a product of prime numbers. So here I have theorem 4.4.5, which is the unique factorization of integers theorem, otherwise known as the fundamental theorem of arithmetic, which says given any integer n greater than 1, there exists a positive integer k, distinct prime numbers p sub 1, p sub 2, and so on up to p sub k, and positive integers e sub 1, e sub 2, and so on up to e sub k, such that n equals p1 to the e1 times p2 to the e2 times p3 to the e3 times, and so on up to p sub k to the e sub k. And any other expression for n as a product of prime numbers is identical to this, except perhaps for the order in which the factors are written. Now, we're not going to be focusing on the uniqueness part of this theorem. We're focusing primarily on the existence part of the unique factorization of integers theorem. This is a really important proof to understand, especially with strong mathematical induction. And if you're interested in mathematics at all beyond discrete math, this is a very important theorem. Now, this proof will require strong mathematical induction. Now, let's first identify what P of n is here. Now, this is going to be a little weird to look at, but P of n is really long. It's everything except this universal quantifier here. We don't want to include the universal quantifier in the predicate P of n. In this case, the predicate P of n is there exists a positive integer k, distinct prime numbers p sub 1, p sub 2, and so on through p sub k, and positive integers e sub 1, e sub 2, up through e sub k, such that n equals p sub 1 to the e sub 1 times p sub 2 to the e sub 2, and so on up through p sub k to the e sub k. That entire chunk is going to be our P of n. Now, this is going to be a bit weird, but we're only going to have one base case to prove in this strong mathematical induction. In the previous few videos, I've shown you examples where we apply a recursive definition of a sequence in the inductive step. And in those videos, we ended up proving multiple base cases because of the gap between the largest index in the recursive definition of the sequence and the smallest index in the recursive definition of the sequence, which usually was 2. We don't have a recursive definition of a sequence, though, in this video. In this video, we're only going to need one base case, which is when n equals 2. So what is P of 2? Now, this is going to look a little weird, but P of 2 is the statement that there exists a positive integer k, distinct prime numbers p1, p2, so forth up to p sub k, and positive integers e sub 1, e sub 2, up through e sub k, such that the number 2 equals p sub 1 to the e sub 1 times p sub 2 to the e sub 2 times p sub 3 to the e sub 3 times, and so on, times p sub k to the e sub k. So this is a little tricky because there's a lot going on, and normally the base case is supposed to be pretty straightforward, like supposed to be something super obvious, like this number is less than this number, and it should take like 2 steps to prove. And it's usually something really small that we're proving, but this is a lot of words. And keep in mind, we need to include a question mark at the end just to avoid asserting the truth of anything. We don't want to assume that this is true. We want to prove that this is true. Now, what exactly are we proving? We're proving that there exists a positive integer k. In this case, we're going to pick k equals 1. There's also distinct prime numbers p1, p sub 2, and so on, p sub k, and positive integers e sub 1, e sub 2, and so on up through e sub k, such that 2 equals p sub 1 to the e sub 1, and so on. So in this case, k equals 1, and because k equals 1, then that means there's only one prime number, and in this case, the prime number is going to be 2, and there's only going to be one positive integer e, in this case e sub 1, which is going to be 1. And so in this case, 2 equals p sub 1, which is 2, to the 1th power. And so we've proven that this is true using this specific k and this specific p sub 1 and this specific e sub 1. That is the base case. Now let's move on to the inductive step. The very first part of mathematical induction, both strong and weak mathematical induction, is always the same. I always start with let k be a fixed arbitrary integer such that in strong mathematical induction, k has to be greater than or equal to the largest base case. In this case, there was only one base case, and so the largest base case is 2. So k has to be greater than or equal to 2. And we're going to assume that p of I is true for all integers 2 less than or equal to I less than or equal to k. So if k is 5, for example, then that means we're assuming that p of 2 is true, p of 3 is true, p of 4 is true, and p of 5 is true. Whereas in mathematical induction, not strong mathematical induction, but weak mathematical induction, we would only be assuming that p of 5 is true, and we would only be using p of 5 to prove that p of 6 is true. In this case, we get to assume that p of 2 is true, p of 3 is true, p of 4 is true, p of 5 is true, all the way up to p of k, whatever k is. Keep in mind it's a fixed arbitrary integer. It could be 2, it could be 10, it could be 10 million, who knows. But k is fixed, which means that there are a fixed number of integers between 2 and k, which represent all of the values of the index variable I. Now, put simply, this means that we're assuming that p of 2 is true, although we've just shown that p of 2 is true in the base case. And this means that 2 can be factored with a prime factorization, and we already showed that. And we can also factor the number 3, and we can factor the number 4 using a product of prime numbers only, and so forth, all the way up to p of k. Even the integer k, which could be 10 million, even that integer can be factored as a product of prime numbers. That means that all of these numbers can be factored into factors of prime numbers. Now we have to be careful with p of k plus 1 because if you remember in the base case, I mentioned that p of 2 says that there exists a positive integer k. This k is a local variable in that it only extends to the base case. This integer k is distinct from this integer k in the sense that these are two completely different parts of the proof. And so the variable k in the inductive step is only local to the inductive step. But because of that, I can't say that p of k plus 1 is the statement that there exists a positive integer k. I can't use k there. I'm going to use a different letter j. So p of k plus 1 is the statement there exists a positive integer j, distinct prime numbers p sub 1, p sub 2, up to p sub j, and positive integers e sub 1, e sub 2, up through e sub j, such that k plus 1 equals the product of those prime numbers. So we need to somehow find a way to factor k plus 1 into factors of only prime numbers. And we can use our inductive hypothesis to prove this. We're assuming that we can factor 2, we can factor 3, we can factor 4, we can factor every number up through k into factors of prime numbers only. We need to show that we can factor k plus 1 into prime factors only. Now I put a question mark here because I want to avoid assuming the conclusion. If I make this a question, then I'm no longer asserting the truth of anything. And so this is the thing that we want to show. We want to show that this is true. Now the key to this proof is absolutely crucial to know in order to be able to apply the strong mathematical induction here. And once you understand the trick, the rest of this proof is actually pretty straightforward and simple. The trick here is to split this proof up into two different cases. And we're going to prove that this p of k plus 1 is true in both of these cases. These cases are going to be dichotomous, meaning that one of these cases has to be true and both of these cases are mutually exclusive. Case 1 is going to be the instance in which k plus 1 is a prime number. Case 2 is going to be the case where k plus 1 is not a prime number. No matter what, one of these cases has to be true, since they're negations of each other. Now, by splitting this up into two different cases, this proof becomes very straightforward. We can say that j, which is this integer here at the top, j is going to be the integer 1. We're only going to need one prime number here. And that prime number, p sub 1, is going to be k plus 1. since by this case assumption, k plus 1 is a prime number, and e sub 1 is going to be 1. And so then k plus 1 equals p sub 1 to the e sub 1, which shows that k plus 1 is a product of prime numbers. We can write k plus 1 as a product of prime numbers. And so that means that there does exist a positive integer j, that j being the number 1. Distinct prime numbers p sub 1, p sub 2, up through p sub j. Since j is only 1, that means there's only one prime number, and that being, in this case, k plus 1, since k plus 1 is a prime number. And positive integers e sub 1 up through e sub j. J is only 1, so that means there's only one positive integer e. And in this case, e sub 1 is 1, since we only need one factor of that prime number k plus 1. And therefore, k plus 1 is a product of prime numbers, which means that p of k plus 1 is true in this case. Now let's move on to the trickier case, which is when k plus 1 is not a prime number. Now, what does it mean for an integer to not be a prime number? Well, that just means that k plus 1 is a composite number. What does that mean? That means k plus 1 can be represented by the product of two numbers. I'll call it a and b. So since k plus 1 is a composite integer, that means k plus 1 equals a times b for some integers a and b, such that 1 is less than a, which is less than k, and 1 is less than b, which is less than k. This just means we can find two factors. Now, it might not be the case that a and b are prime numbers. It might be the case that a and b are also products of prime numbers. It could be the case that a and b can be represented as products of prime numbers. However, what we do know is that a and b satisfy these two inequalities, which is super convenient for us because in our inductive hypothesis, we know about integers in that region between 2 and k. We know that all of those integers can be represented as a product of prime numbers. So since k plus 1 is a composite integer, then that means by definition k plus 1 can be represented as the product of two integers a and b, such that 1 is less than a, which is less than k plus 1, and 1 is less than b, which is less than k plus 1. Now this means that a satisfies the inequality 2, which is less than or equal to a, which is less than or equal to k, and 2 is less than or equal to b, which is less than or equal to k. Now we know about integers that satisfy this inequality. In this case, we know that so long as I is some integer between 2 and k, then p of I is true, which means that we can factor those integers as a product of prime numbers. So that means that we can apply the inductive hypothesis to a and b. Now, since a satisfies this inequality here, then that means that by the inductive hypothesis, and I'll put here by IH, which means by the inductive hypothesis, that means that there exists a positive integer q. I'm using a different local variable here. Distinct prime numbers a sub 1, a sub 2, and so forth up through a sub q, and positive integers l sub 1, l sub 2 up through l sub q, such that a equals a sub 1 to the l sub 1 times a sub 2 to the l sub 2 times and so on up through a sub q to the l sub q. This is simply saying that a can be factored as a product of just prime numbers and only prime numbers here. We could do the same thing with b because we know that b satisfies the same inequality, which means that by the inductive hypothesis, there exists a positive integer r. I'm using a different local variable here. Distinct prime numbers b sub 1, b sub 2 up through b sub r, and positive integers s sub 1, s sub 2 up through s sub r, such that b equals b sub 1 to the s sub 1, b sub 2 to the s sub 2 times dot 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 times b sub r to the s sub r. So both of these are true because of the inductive hypothesis. So we know that p of a is true and p of b is true, and we're still in case 2. Keep in mind we've already done case 1. So in case 2, k plus 1 is a composite integer, and that means we've represented k plus 1 equals a times b. But now we know what a and b are. So we can say that k plus 1 equals a times b So this means that a times b equals a sub 1 to the L sub 1 times a sub 2 to the L sub 2 times dot 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 times a sub q to the L sub q. That's the a part. And then b can be substituted with b sub 1 to the s sub 1, b sub 2 to the s sub 2 times dot 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 times b sub r to the s sub r. This result is a product of prime numbers. And this is because a sub 1, a sub 2, all of those a sub whatever number, a up to a sub q, all of these are prime numbers. And same thing with b sub 1 and b sub 2, all the way up to b sub r. We have here a product of prime numbers, which means that k plus 1 can be expressed as a product of prime numbers. Therefore, p of k plus 1 is true. Now keep in mind, we've proven that p of k plus 1 is true for the second case here. There's two cases. Case 1, k plus 1 is a prime number. But we showed that p of k plus 1 is true under case 1. Under case 2, which is the negation of case 1, we have shown that using the inductive hypothesis, we have shown that p of k plus 1 is true, which means we can factorize k plus 1 as a product of prime numbers only, which is what we did here. And we use the inductive hypothesis here. That was absolutely crucial in this proof. In either case, we have shown that p of k plus 1 is true. And so p of k plus 1 is true either way. And so this means that, therefore, by mathematical induction, p of n is true for all integers n greater than 1. So that means every integer greater than 1 can be written as a product of prime numbers, which is a very important theorem. And I think that there's a lot of letters in this proof, but really the idea of writing k plus 1 as a product of two numbers where we can apply the inductive hypothesis to these two smaller numbers. These numbers are both smaller than k plus 1, and they're both bigger than 1, which means they satisfy the exact inequality that must be satisfied in order to be a part of the inductive hypothesis. The inductive hypothesis says that we're assuming p of I is true for all integers 2 less than or equal to I less than or equal to k. That includes the integers a, and that includes the integers b, and so we apply the inductive hypothesis to a and b, and then we use substitution, which I probably could have said here by substitution. We can express k plus 1 as the product of prime numbers only. All of these numbers, a sub 1, a sub 2, up through a sub q, b sub 1, b sub 2, up through b sub r, are all prime numbers. Thanks everyone, and I'll see you in the next video.